up, guys? This is 7-4 in Advanced Geometry. Today we're talking about a little more similar triangles and a little simplifying radicals. So here in these real life situations, we use similar triangles to estimate really tall things like trees or flagpoles or whatnot. So to estimate the height of a tree, Big Willie waited until his and the tree's shadows coincided. That coincided just totally means that they're like on top of each other. So let's check it out. We got this triangle right here for Big Willie, and we've got this triangle right here for the tree. And it just so happens that these are similar triangles because we've got a shared angle right here, like this angle is both pink and green at the same time, and because we assume that the ground is flat and things are perpendicular to the ground, that we'll assume that those are right angles, so we'll have an angle-angle situation. And that's why these are estimates, because we all know that the ground isn't always flat and trees aren't really perpendicular all the time, but they're pretty close in most scenarios. So check it out. Big Willie is 7 feet tall. Let's put that in our picture, 7 feet. And his and the tree's shadows are 8.25 feet and 19.25 feet, respectively. What respectively means is in the order that they just told you. So they told you his shadow comes first and 8.25 comes first. The tree's shadow is second and the 19.25 comes second. So the real trick is where the heck are shadows located when there's nothing in the way? Aren't shadows located on the ground? So Big Willie's shadow is this in feet, and the tree's shadow, it's not really just this orange part. Like, that's part of the tree's shadow, but the tree's shadow is really this entire distance because Willie and the tree's shadow are right on top of each other, so they lined it up that way. So this is 19.25 feet, the whole honker of a distance. So because these are similar triangles, we can set up a scale factor. We know both these sides correspond to each other, and we'll do big over little. So 19.25 over 8.25, and we want to find the height of the tree. I guess we should probably call that x in this situation. That would correspond to this 7, so we'll do big over little also. And don't worry about trying to reduce this scale factor thing. It's all going to work out nice and neat if we just leave them the way it is. So we'll do a little cross multiplying. 19.25 times 7, boom, 134.75, and that'll equal 8.25x. And to solve for x, we just divide by 8.25. So divided by 8.25, and that actually comes out nice and exact, 16 1/3. But the funny thing is a couple reasons. One, they say round the height of the tree to the nearest foot. And the other thing is that even though algebraically that was exactly 16 1/3, remember, this is just an estimate. We really don't know if the ground's perfectly flat or if these are perfect right angles, so it's going to be close to this 16 1/3 feet. And when they say round to the nearest foot, honestly, it doesn't matter if you round up or round down in this situation, because you can make an argument for 16 feet and you can make an argument for 17 feet. Sometimes you don't really have a choice of when to round, but in this case, I'm going to just say that's about 16 feet. And if you had 17 feet, there's nothing wrong with that either, because you got an argument both ways. So let's try the next one. Farmer Brown was curious how tall his family's 100-year-old grain elevator was. He aligned himself with the shadow of the grain elevator and measured his shadow to be 7 feet, while the grain elevator shadow was this, and Farmer Brown is this. How tall is the grain elevator to the nearest inch? First, show me that you know that these triangles are similar by putting these markings in there. You've got this shared angle between these two triangles, and you've got the perpendicular fact of this is like where the ground is. Okay, so we're assuming things. It says that his shadow, so we're talking about Farmer Brown's shadow, is 7 feet. And the grain elevator shadow is 63 feet 4 inches. So we'll put all of that in this big honker, so 63 feet 4 inches, and oh no, we've got a problem of feet and inches, and Farmer Brown is 5 foot 7 inches tall. Another problem. There's lots of ways you could set up a proportion to find the height of this grain elevator, all that stuff, but because they mix things up into feet and inches and all that crazy stuff, I like to just convert everything into the smaller unit, which is inches. So I'm going to change all this stuff into inches. So 7 feet first. Since there's 12 inches in a foot, we'll take that times 12 and get this guy to be 84 inches. 63 feet 4 inches. I just need to change the 63 feet into inches, so I'll take him times 12, and that's 556 inches, just this part right here. So I need to add another 4 and say this whole length is 760 inches. And 5 foot 7 inches, I'll take the 5 times 12 and get 60 inches, plus the other 7. Farmer Brown is actually 67 inches tall. And now that we're in the same unit, I can set up my scale factor because I have similar triangles. So big over little, 760 over 84. Make sure you guys are using the right numbers and you don't mess things up and use one of them in inches and one of them in feet. That'll be x over 67. And we'll solve with cross multiplication. 760 times 67. And please put a comma in that large number. 50,920 equals 84x. And we'll divide by 84. And that's about 606.2. I like to actually kind of just say what it was to the nearest tenth, and then round how they tell me to round in these situations. They say round that to the nearest inch. So again, if you had 606 inches or 607 inches, it really doesn't matter because they're both kind of appropriate. So to answer this question, it's about 606 inches tall. But dude, nobody talks like that in the real world. Like, how tall is your grain elevator? Oh, 606 inches. Why don't we change that back into feet and inches by dividing him by 12? So that is about 50 feet and 0.5 feet, right? So 50 feet and half a foot, isn't that totally 6 inches in that situation? So that grain elevator is about 50 feet, 6 inches tall, approximately. So pretty simple story problems. Now we'll do a little simplifying radicals, and some of this you've done before. You have seen, like, step number 1. There's 3 major rules of how to simplify radicals, and you've done step 1 before, but we'll refresh your memory. Please write your first 15 perfect squares down the side of your paper. You can pause the video to do that real quick, so get those copied down. Alright, and now to simplify a radical, it's the same thing as like simplifying a fraction. Like if I gave you a fraction of 4/8, you all know that that can simplify, but it's kind of interesting if you've ever actually seen it simplified the correct way. 4 is a number that goes into both of those, so you really break this up to be 4 times 1 over 4 times 2, and you can like totally cancel out the 4's in that situation. So that simplifies to be 1/2 in that scenario. But if I asked you to reduce this fraction and you did something like this, like 2/4, yeah, you did reduce the fraction, but you didn't completely reduce it. So we're going to do the same thing with these radicals. We got to make sure we completely reduce them, because rule number 1 is you can't have a perfect square multiple underneath a radical. So I'd like to see if there's a perfect square, actually not just a perfect square, but what's the biggest perfect square, because you could have more than one, that goes into 50 evenly. So on this list that we have right here, I can see that 64 is actually the first perfect square that's too big. He's bigger than 50 in that situation. So I work myself backwards to see who's the first perfect square that goes into 50 evenly. So if I take like 50 divided by 49, that doesn't come out nice as a whole number. 50 divided by 36 doesn't come out nice, but 50 divided by 25 is totally coming out nice. So 25 is the perfect square, the biggest one that goes into 50 evenly. How many times? Twice. These two numbers totally multiply together to be 50. But now we simplify it just like I did right here, like I totally just factored out a 4. Then you clean this part up right here. Well, I can clean this up. I know what the square root of 25 is. He's 5. And then the square root of 2, that doesn't simplify at all. So that square root of 50 is the same thing as 5 square roots of 2. So we'll do that again to square root of 27. 36 is actually too big. I'm going to work backwards. 25 doesn't go into 27. 16 doesn't go into 27. But 9 does. So 9 goes in there 3 times. And I can simplify the left side. Always put the perfect square on the left side. So 3 square roots of 3 is what that thing totally cleans up to be. And when we learned this for the first time back in the day, square root of 72 gave us a lot of problems. Reason why is because 4 goes into 72 evenly and 9 goes into 72 evenly, but that's not the biggest perfect square that goes into 72 evenly. Work your way backwards and figure out that 36 is the biggest perfect square that goes in there evenly. It goes in there twice. So this actually becomes 6 square roots of 2, which is totally like the same yet different is saying, well, what if you said 9 went in there 8 times? Well, yeah, 9 does go in there 8 times, and that can become 3 square roots of 8, but that's not simplified. That's like when I said simplify 4/8 and you gave me 2/4. It's like, dude, that can keep simplifying. So you could simplify this again, because 4 goes into 8 twice, and you could call that 3 times 2 times the square root of 2, and that's really 6 square roots of 2. So you can eventually get to the right answer, just like you said, oh, that's 4/8, which is 2/4, which is the same thing as 1/2. I mean, you can reduce and reduce again. Just make sure you have completely reduced. So 5 square roots of 24. Just let that 5 tag along, and let's simplify the square root of 24. Find the biggest perfect square that goes into 24 evenly. So you work your way backwards, and 1 never counts. 1 goes into everything, dude. You know, so it's like 1 doesn't count. So 16 doesn't go into 24, 9 doesn't go into 24, but 4 does. And it goes in there 6 times. So doesn't that become 5 times 2 square roots of 6, which is really 10 square roots of 6, because you can multiply those guys together. And you could take radicals times radicals if you wanted to. You could multiply these together, or you could simplify them separately, one at a time. It doesn't really matter which way you do it. You could take radical 20 times radical 2 and get radical 40 if you wanted to, and then try to find the biggest perfect square that goes into 40 evenly. So why don't you pause the video and try to get that done. And I hope you figured out that 4 is the biggest perfect square that goes in there 10 times. Isn't that 2 square roots of 10? So that's one way you could do it. You could also simplify this first and see if that simplifies and then multiply them together, and you'll still end up getting the right answer. Here, radical 12 times radical 3 is totally radical 36. And these are so brain farty. It's like, dude, this is the square root of 36. That is a perfect square, right? So the square root of 36 is 6. Like, that's so easy that we might brain fart. When you get a perfect square underneath the radical, you're finished. Just square root him. And now let's solve for x. This is a right triangle where we know 2 sides of the right triangle. We're missing the 3rd side, so we can do the Pythagorean theorem. So 3 squared plus 3 squared should equal x squared. Remember, the hypotenuse is always the guy that goes all by himself. 3 squared is 9. And do it again, it's 9. And that's x squared. And 9 plus 9, 18. And now that we got 18 equal to x squared, we can get rid of the square by square rooting. Doesn't that equal the square root of 18? Should be plus or minus, but we don't use the minus due to the fact that we're finding a distance, so it can't have a negative distance. So just square root of 18. But that can simplify. So find the biggest perfect square that goes into 18 evenly. 16 is too big. 9, oh yeah, goes in there twice. So isn't that really 3 square roots of 2 equals x? So set up the Pythagorean theorem for this guy. Pause the video, solve for x, simplify the radical. So the hypotenuse goes by himself all the time, all by himself. So 4 squared plus x squared should equal 6 squared. And then we'll square everything and get 16 plus x squared equals 36. Let's get x squared all by himself by subtracting, so x squared equals 20. Then we'll square root both sides, and x equals the square root of 20, and we only need the positive, but he can simplify. Isn't the biggest perfect square that goes into 24, and it goes in there 5 times. So x is actually 2 square roots of 5 in that situation. So all of that we've done before. No big deal. But now here's some new rules. Rule number 2, you cannot have a fraction underneath the radical. And you can't change it to a decimal either. Radicals and decimals don't go together either. So can't have a fraction underneath the radical. Well, that's simple. Just pull them apart. Just totally put the numerator with a radical around it and the denominator with a radical around it. So change it to like radical 2 over radical 7. That solves that problem big time. No more fractions underneath the radical. But now we've got a bigger problem. Rule number 3 is you can't have a radical in the denominator of this fraction. So we're going to get rid of him with some math magic, baby. We are totally going to multiply this number by the number 1. Because if you take somebody times the number 1, you don't change his value, right? You're keeping him the same. But to make this radical in the denominator disappear, we're going to use a very fancy form of 1. Like, isn't radical 7 the bad guy in this situation? Can't have him down here? So we'll multiply by radical 7 over radical 7. This red number is totally the number 1, right? Radical 7 divided by radical 7 is 1. So we're going to take the blue number times 1 and keep him the same. But we're going to solve our problems with math magic. So let's see what happens. Numerator times numerator, radical 2 times radical 7 is radical 14. And denominator times denominator, radical 7 times radical 7 is radical 49. But dude, we probably shouldn't write it like that, because square root of 49 is what that says. The square root of 49 is actually the number 7. And alakazam, we just solved our problem. We got rid of the radical in the denominator, because radical 7 has radical 7 turned out to just be plain old 7. So let me show you a couple more of those. If you had like radical 5 times radical 5, dude, that's radical 25. This pen, sorry about that. But radical 25 is actually just the number 5. It's the square root of 25. Just like radical 3 times radical 3 is going to turn out to be radical 9, but we usually just call that 3 in that situation. Because, dude, we're taking the same thing times itself. When you take the same thing times itself, it's like squaring it. And squaring a square root, they cancel each other out. So you're just left with that number underneath there. So that's pretty cool. So that's how we got rid of the radical in the denominator. Then we got to check to see if this is still simplified. It might still reduce further. So there's no there's no fractions underneath the radical. The only thing underneath there is 14. Like, he's fine. This fraction has nothing to do. It's like inside that square root symbol, it's just a 14. There's no radicals in the denominator, so we're cool there. And like the square root of 14 doesn't simplify either, so this is our final answer. Let's do another one of those. Problem. We've got a fraction underneath the radical. Pull them apart. Square root of 16 over the square root of 5. Pull them apart. And now slow down. We have a problem down here. We can't have that radical in the denominator, but look at this. What a beautiful sight right there. I've got the square root of 16, and we might as well just clean that up and make our life a whole lot easier. Isn't that really the number 4? So I got 4 over the square root of 5, and we have to use math magic, which is really called rationalize the denominator, but I just like to call it math magic. Instead of multiplying by radical 7 over radical 7, now isn't radical 5 the problem, so we'll multiply by himself, like over the top of each other. This is the number 1. So we're going to take this times 1 and not change any values. So upstairs, 4 times radical 5. Well, they don't play nice whole numbers and radicals. They just have to sit next to each other and be happy about it. So 4 square roots of 5. And radical 5 times radical 5 is just going to be 5. It's really the square root of 25, but we might as well just go ahead and call that 5. So we check. There's no fractions underneath the radical symbol. There's no radicals in the denominator. Radical 5, this guy doesn't simplify at all. He's as clean as a whistle. But you also got to check these numbers here to see if they reduce. And 4 over 5 doesn't reduce, so this is our answer. So let's do another one. Pull this guy apart. You can't have a fraction underneath a radical. Then we got a radical in the denominator, so we'll get rid of him by multiplying by the number 1 in the form of the problem over itself. So numerator times numerator, radical 3 times radical 2 is radical 6. And denominator times denominator, radical 2 times radical 2 is radical 4, normally known as 2 in that situation. And then nothing else cleans up. No fractions under here, no radicals down here. 1/2 doesn't simplify, and the square root of 6 doesn't simplify. So, done. Here, problem, radical in the denominator. Get rid of him. Why don't you pause the video and multiply by radical 3 over radical 3. And upstairs, you should have got 12 square roots of 3. Downstairs, radical 3 times radical 3 is 3. And yo, dude, we can clean up this 12 over 3. It's like 4 over 1. So you get 4 square roots of 3 all over 1, which you don't need to put that anymore. And then these last two, they kind of give people an issue because they're not sure who the bad guy is. A lot of people think that 5 square roots of 3 is the bad guy. 5's okay. we don't care about 5. Like 5's not an issue for us. It's the radical 3 that's really the bad situation right here. So all we have to do to get rid of that radical in the denominator is only multiply by the problem. Like the 5's cool to be down there. It's just this radical 3 that's not cool. So we'll only multiply by that. So 3 is a whole number. He doesn't have anybody to play with. But these radicals can multiply together. So that's going to be radical 6. And then down here, you got 5, who's a whole number. He didn't have anything to play with. But radical 3 times radical 3, that's just going to be 3. And then we just look to see if anything can clean up. And yep, I got a times 3 upstairs and a times 3 downstairs. Those can cancel. So I got radical 6 over 5 in that situation. And the last one of these looks like it could be really hard, like radical 30 is a problem, but dude, we can totally clean that up. You can clean up a radical over a radical, like radical 10 over radical 30. That can totally reduce to be like radical 1 over radical 3. You can reduce radicals with radicals just like you can reduce numbers with numbers. So the only thing is there was still a 3 down here that we haven't put. So we got an issue. We've got a radical in the denominator. Also, I see the square root of 1, so I can make him be 1. And to get rid of this radical in the denominator, now I can just multiply by an easy little guy like radical 3 over radical 3. So numerator times numerator over denominator times denominator. I got 3, and then it'll be times this, which is also 3. So if you want to just go ahead and call that 9, I'm fine with it. If you want to write 3 times 3 and clean that up, it's all good. But there you go. And these don't reduce. You can't reduce radicals with whole numbers. They don't play nice. So let me know if you have any questions, guys. Have a good one.